Okay, so let's begin. Now, what we talked about last week, a little bit more than last week, we started off with a little bit of review. Now, first off, this is something you've seen before. This is the point 0, 0. This is something you've seen before. This is called the coordinate grid. Coordinate grid. It can also be known as the coordinate plane. Either one works. Okay, I tend to say coordinate grid. So this is the coordinate grid. It has two components, right? It has the x-axis, right, that goes side to side, and then I'll put that over here so it's a little more obvious. The x-axis, and then we have the y-axis, which goes up and down. Every coordinate on the coordinate grid follows a pattern where we list a number x and a number y, right? So if I have 2, 3, that tells me to go over 2, right? 2, it goes over 1, 2 to 2, and then we're going to go up 3, 1, 2, 3. We plot our point right there, over 2, up 3. Right? That should be reviewed. That's 5th grade material, but it's good to review it, right? Note, however, that x and y, right, you might not have been introduced to them as such. X and y are really just two variables, right? Whenever you're dealing with something, whenever you're dealing with two variables at a time, x and y just tells you the value of those two variables. So this coordinate here tells us that x is equal to 2 and y is equal to 3, right? It just tells you the value of those coordinates. So if I plot a point right here, well, that tells us that this value has an x of equaling 4 and a y of equaling 5. And we represent that with just 4, 5, this ordered pair. Okay, this ordered pair of numbers, that's what this is called, an ordered pair. It can often be just referred to as a coordinate, though. So that's what that means. But as we've seen in our algebra, x and y don't necessarily have to take on positive numbers. In fact, they could very easily, and often are, negative numbers. So how do we represent a negative number here? If I were to give you the coordinate 3, negative 2, what would that look like? Right? Well, we have to sort of expand our vision. So I'm going to slide over. This is the coordinate grid that we are going to be using in this class and Modules going forward. Still has the x-axis, still has the y-axis, right? But the x-axis and y-axis go further than they did before. They go all the way into the negatives in both directions, right? They go into the negatives in both directions. So when I look back, what was that coordinate? 3, negative 2, if we're talking about 3, negative 2, it's the same idea, right? So we're going to go over 3, 1, 2, 3. We're going to go over 3 on the x-axis. But then rather than going 1, 2, up to positive 2, we're going to go down to negative 2 right here. So this point is 3, negative 2. Its x value is 3, and y is equal to negative 2. There we go. All right. So that's sort of that's about all of it when it comes to graphing on a coordinate grid. But when we talk about the coordinate grid, there's a few terms that you need to know. First off, the point right where the two axes cross, right, where the x-axis crosses with the y-axis. Now this would be the coordinate 0, 0, and it gets a special name. It's called the origin. The origin. You can sort of think of it, it's where the graph stems from, right? It's the center of the graph, it's the origin of all the axes, so on and so forth, right? So that is the origin. Now, each of these little areas going around the side, right, there's sort of an area here, there's an area here, there's an area here, and there's an area here. Each of them gets their name. It's their own name. So this is called quadrant, and take a second, guess why it's called quadrant. This is called quadrant 1. right? This is called a quadrant because there's 4 of them, there's 4 quadrants. The way we number them, we just sort of go counterclockwise. So this is quadrant 2, this is quadrant 3, and this is quadrant 4. All right? 1, 2, 3, and 4. Now, there's some sort of patterns you can notice about each quadrant. In quadrant 2, the x values are all negative, right? Because you're to the left of this, all your x values here are negative. So you know that doesn't matter what coordinate you're talking about. If you're in quadrant 2, the x value is going to be negative. And the y value, because we're up here, is going to be positive. In quadrant 3, because they're both talking about negative values, they're going to be negative and negative. Doesn't matter what the numbers are, they're both going to be negative. And in quadrant 4, because we're positive x but negative y, we're going to be looking at something like this, positive and negative. Okay, so that's always going to be true for these quadrants. This coordinate up here, right, quadrant 1 is just our typical positive, right, always positive. Okay, that's about all the anatomy of a coordinate grid that you need to know. Now it's really just a system of practice. So before we jump into the practice, I want you to think to yourself, this blue dot, what is the coordinate for this blue dot? Now, I want you to be careful here. There's a few common mistakes that can be made. First off, this is not -3, -1. I want you to think, why isn't it -3, -1? Well, this isn't -3, -1 because we don't go down first, right? We go over first. So this should rather be -1, -3, right? So be careful with that order. That's a really easy mistake to make. The first number always represents your x. It always represents how far side to side you are. Then the second number always represents how far up and down you are, right? So if I have this -3, that's telling me that I'm to the side -3, not down. That's not good. That's not what I am, right? So we know that this blue coordinate here is -1, -3, because it's the left -1 and it is down -3. Okay, first thing, set of homework. I want you to try, first off, plotting these sets of points. So you've got 6 points here. I want you to, maybe you can draw this out on your own piece of paper and plot where those points go. So put them where they are and then label them so I know which one you're talking about. Okay. After you do that, I want you to, for each point, tell me which quadrant those belong to. All right. You can reverse the video back if you need to, but tell me which quadrant is each of these points in. Now, I will tell you some of this they are in neither quadrant. They aren't in any quadrant. So if that's the case, you can tell me that as well. Okay, moving on. Now, when we're talking about the quadrant or the coordinate grid, there's some important things to be able to talk about. First of all, if I have these 2 points, let's say A and B, it can be very helpful to talk about how far apart they are. What is the distance from A to B, right? So what is the distance from A to B? In asking that question, the most obvious and direct way in order to find that is figure out, well, how far do you have to go from one to the other? So if I'm starting at A, I have to go 1, right? From go to 4 to 3, I gotta go down another. There's 2, so 1, 2. Then I gotta go down a third, and then I gotta go down another time 4, down another time 5, and then down till I hit 6, right? So they are 6 apart. The distance from A to B is 6. Now you can sort of do that counting, and that works, right? But there can be faster ways to do that, right? Rather than counting point by point, right? So if I were to ask you the distance from B to C, right? The distance from B to C, well, we could just start counting, oh, we gotta go 1, 2, 3, so on and so forth. But it can be helpful to look at what these points actually are. Well, first off, I know that this is -1, -2. And I know this point C is +6, -2. Right? So when I'm looking at this x component, here x is equal to -1, and here x is equal to 6. Their y values are the same. They're both -2. So rather than sort of counting step by step the way through it, I can think, well, how far apart is -1 from 6? How far apart is -1 and 6? Right? Well, they are 7 apart, right? You have to count 7 up to get from -1 to 6. Another way to think about that quicker is, well, how far do I have to go to get to 0 from x? So from this, from -1 to 0, is just a distance of 1, right? From 6 to 0, I have to go a distance of 6. So I have this 1 and 6. So if they were to sort of meet up on the x-axis right here, or sorry, the y-axis, one would have to go 1 and the other one would have to go 6, right? So the total distance is 7. Yeah. 1 and then 6 combined makes this whole distance 7. Now you have to be careful though, because if they're on the same side of the x-axis, you don't really want to do that. Here, these are just, C and D are just 1 apart, even though one's 2 from the x-axis, one's 1 from the x-axis. So they're both, you don't want to add those, right? You actually want to subtract them. So it takes a little bit of critical thinking, but this is something I don't think you'll struggle with very much. So it's just for finding the distance between 2 points, right? So here, in homework 2, I want you to find the distance between these 2 points, A to B, B to C, C to D, and D to E. Now, it might be helpful to, plot out a coordinate grid, put these points there, and sort of just count. How far do I have to go? How many spaces do I have to go to get from A to B and B to C and C to D? But with E, right, E is -1,000,000. You're not going to be able to count that by hand. So you have to sort of think critically, well, how far is -1 from -1,000,000, right? How far are those two numbers apart from one another? Right? So try that. I think you should do well on it. Okay, so that's about as much as we've covered in the coordinate grid. We did a few other practice things on it, but that's all the things that you need to know. The rest of the time, we spoke a lot about area. Now, what is area, right? It's a word we know. You probably know how to calculate it, right? You probably know length times width. A is equal to length times width, and that gives you a number. But what does it mean, right? What does the area mean? Take a moment. I want you to think about how you would articulate that. How would you put that into words? What is the area? What is it telling us, right? So here you might know that the area is 8. But what does that number tell you? Think for a moment. Okay. So, yes, 2 times 4 does equal 8, but what does 8 mean? Well, the area really is telling us how much space is there inside a shape. More than that, though, it doesn't just tell us how much space there is. Well, it does tell us that. It's more specific. What it's really telling us is how many squares can we fit in here, right? If we think of 2, well, here's 1 and here's 2, right? We can sort of break that into 2 pieces. And here we can break this into 4 pieces, 1, 2, 3, and 4, right? The area tells us how many squares we can fit. How many 1 by 1 squares can we fit into this shape, right? This is 1 and this is 1. Well, here we can fit 1, 2, 3, 4, 5, 6, 7, 8, right? That's why the area is 8. Yeah, that's why the area is 8. Is because there are 8 of these squares that we can fit in there, 8 1 by 1 squares. The calculation 2 times 4 isn't just something that's made up. It's sort of obvious when you think about it that way, right? Well, there's going to be 2 rows with each row being 4 long, right? So 2 times 4, 4 2 times, right? Now, as we move on to more complicated area problems, which we're going to do here in just a moment, that definition doesn't change. It's still asking the same thing. How many squares can we fit in there, right? We're going to talk about a variety of shapes. So this is, we just spoke about just a second ago. This is a rectangle, right? A rectangle. A rectangle has a length and a width. The area is equal to length times width. Now, this is something you've seen plenty of, so I'm not going to waste time on it. But we're going to talk about 3 more shapes. Now, take a moment, see if you can remember what these are called. I'll start with the obvious one. This is a triangle, right? This is called a parallelogram. Parallelogram, because both sides are sort of parallel to one another. They point in the same direction. Parallelogram. And then last week we have a good old trapezoid. The trapezoid sort of has a long side and a short side that are parallel with each other, and then 2 more sides that connect them. Okay, now we're going to find the area for each of these shapes. So to begin, let's talk about the parallelogram. I want to sort of talk about where the area might come from this. We're looking at this, right? And we don't really have a formula right away, right? But there's something we can do to this parallelogram to make it sort of obvious on how we can solve it. We can cut this triangular piece off the end, right? This piece that is moving side to side, we can cut it off the end. We can slide it over and stick it right there. And look, it fits together and it makes a perfect rectangle, right? Now, we have the formula, right? Or we can sort of think, we can figure out the area of this rectangle pretty easily. It's just going to be the bottom, which here is being called B, and then the length, right? Length times width, so B times H, right? We didn't know what this H really corresponded to before, but this is called the height. It's the difference, the distance between these 2 lines, the top line and the bottom line, right? So here it's obvious we're going to take the bottom line and multiply it by this side line. So we're going to take B, this base, and we're going to multiply it by the height, B times H, right? So in practice, that is as simple as taking any sort of parallelogram. This distance along the bottom is B. This distance along going from here up to here, that distance is called H, and the area is equal to B times H. I think I wrote that right here. Sorry about that. Now, so area of a parallelogram is B times H. So if I were to change this to, let's say, 10 and 12, well, then we just take the base, multiply it by the height, and we get 120. 120 is equal to B times H, because this is the base and this is the height. Simple as that. Parallelograms are really easy, right? Sort of skewing this to the side doesn't actually change the area at all. Now, the next shape we're going to talk about, I think we're going to skip right over to triangles. So let's look at a triangle. You know what? I'm actually going to do this, demonstrate this one by myself. So here we have a parallelogram and its dimensions, right? We have a base, and we have a height, and it has some area. Now, if I were to take that area and I were to cut right along here, we can see that I'm sort of cutting the area in half, right? We have half up here and we have half down here, right? I took my shape and I cut it in half. Well, what I'm left with after I cut it in half is a triangle, right? With a base and a height, just the same. But now the triangle is only has half of the area of the parallelogram. So while the formula for a parallelogram is the area is equal to base times the height, the area of a triangle is 1/2 of the base times the height. Right? It is 1/2 of whatever the base is times the height. Right? Now that's a easy thing to forget about, right? So if I were to give this triangle a base and a height, right, a base of, let's say, I'll say 10, and a height of 10, right? So it's 1/2 base times height. If it was the full parallelogram, if this was still this, it would just be 10 times 10 is 100. But because it's only half of that, this half is gone. We don't have that anymore. It's only half that. We're going to do 10 times 10 like we would, and we're going to divide it by 2. We're going to take half of it. So the area here is equal to 50. Right? So that's what you do for all triangles. You take the base and the height, multiply them together, and whatever number you get, divide it by 2. Okay, the last one that we're going to talk about today is the area of a trapezoid. Okay, now this one's a little tricky. So we have this height still, this h going up and down between what they call B1, B2. I'm just going to call those top and bottom. The green line is the top, the red line is the bottom. Now, we still have we have some number of variables here, but how do we solve this? Well, again, it takes a sort of manipulation to get it into a shape that we do know how to solve. We don't know how to find the area of a trapezoid, but maybe we can tweak it in a way to find it, or to turn it into a shape we do know how to solve. The trick here is to duplicate it, turn it into 2 trapezoids, take one, flip it over, stick it right on the side like that, right? So I'll do that one more time so we can see it. I'm taking it, I'm duplicating it, so now I have 2 trapezoids, flipping one of them over, and I'm sort of gluing them together on the edges. Well, now what shape do you have? You just have a big parallelogram again, right? So both the triangle and the trapezoid, both of their areas, right, come from the the parallelogram. Trapezoids and triangles, the formula for those are derived from the formula of a parallelogram. And the formula for a parallelogram is derived from the formula of a square. In math, we often sort of look at these formulas like they came out of thin air, like you had to be some super genius in order to find them out. But a lot of the time, it's really not that far away from what we know to be pretty easy, right? Finding the area of a rectangle is really easy. A parallelogram is pretty much the same as a rectangle, and a trapezoid is pretty much the same as a parallelogram. Okay, enough tangent though. When we duplicate it and flip it over, we have a base along the bottom, and we still have a height, but what are the dimensions of that base? Right, the base now is the whole thing, the bottom and the top put together. Right, the bottom and the top put together, B1 plus B2. The top plus the bottom is now the base. The height remains the same. So we take the B1 and we take B2, we stick them together, we add them together, and we multiply it by the height. And that comes together to form our sort of formula here. We take the bottom number and the top number, we add them together, B plus T, right? That gives us the bottom of our new sort of parallelogram. Then we use those numbers, well, then we just multiply by the height, so I'll indicate with blue. But because we had to duplicate our parallelogram in order to create it, right? To create this new, we duplicate our trapezoid in order to create our new parallelogram. To go back to the area of just the trapezoid, we're going to have to take half of this. So the final thing is 1/2 of the height times whatever the combination of the base and the top will be. All right. Now I know that's kind of a lot, so maybe rewind the video, watch that a couple times if need be, and how that works. But let's go through an example together and what we might get. So rather than variables, let's talk about some specific numbers. Well, let's say this is 12 and this is 10, and let's say the height is 5. We'll go with a nice round 2. Easier number to work with. Well, in order to calculate the area, we're going to take our base, this is our base, and our top, our bottom and our top. We're going to add them together, 10 plus 12. We're going to multiply whatever that product is by 2, and then we're going to take that whole thing, we're going to take half of that whole thing. So here we get 22 times 2 times 1/2. Well, that just equals 22. So the area here is 22. There we go. That's all you got to do. Now, you can sort of practice and memorize this formula, and that'll get you there. But I would say having a deeper understanding why this is true will make that formula stick longer, right? The more you know why something is true, the easier it is to remember it, right? So if you just try to memorize the formula, you might be able to get through the next quiz, but I'm sure you'll forget it after that. So I'd recommend really going back and thinking deep on these things. Okay, for homework 3, this will be from the textbook. I want you to do page 517, all the problems, and do page 523, all the problems. Right, they're just a page each, a lot of just calculating area, just punching numbers into a calculator. I don't think it should take you very long. Okay, now, next subject is composite areas. We can take two shapes. We have a triangle and a square. We can find the area of each, right? This is going to be 1/2 of 20 times 10, which is 100. So this area is 100, and then this is just going to be length times width, which is just 10 times 10, which is 100 as well. So if the square has an area of 100 and the triangle has an area of 100, well, together we have 100 and 100. The area of this shape has to be 200, the combined area, right? That's all we mean is a composite area. Composite means just sort of composed of different things. You'll see that word a lot in your life, but we're just taking multiple things and sort of sticking them together, right? It's a pretty simple idea. Just take any shape you have, right? Any number of areas you can work with, stick them together, and you can create a lot of interesting shapes. It sort of goes. In fact, let's do a quick example. So something like this. Let's imagine this is a little better. Oh, I'm just gonna fix it. Say these are all nice straight lines. Say this is 10. This is 10. And these are both 4, right? Well, there's some deduction that can be made here. If this is 10, right, this whole distance here is 10, well, then these two combined have to be 10. But if this is 4, then this would have to be 6. Similarly, if this is 10, then these two sides combined would have to be 10. But if this is 4, then this over here has to be 6. So now we figured out all those sort of remaining sides that we need to know. But we don't have a formula for this weird shape. However, we can sort of break it into pieces, right? I can sort of draw an imaginary line across here, and now I just have a simple rectangle, right? Which is just going to be 6 times 4 to find the area of that rectangle. Similarly, going around here, I have another rectangle. And this rectangle is 6 times 10, which equals 60. This was equal to 24. So the composite area here is going to be 60 plus 24, which equals 84. We took this complicated shape and we broke it into simple shapes that we knew how to find the area of. Now, you can do that, or you can think of it another way. Instead of thinking, instead of thinking of sort of adding shapes together, we can think of subtracting. If this sort of dent wasn't in this shape, it'd be really easy, right? 40 times 30. But the dent is here, so how do we deal with it? One moment.
Mrs. Howe, dial room 100, please. Thank you.
So here, if we wanted to find the area of this big rectangle, right, we can just do 40 times 30 to get 1,200, right? But we need to take out a sort of chunk. We have to take out this sort of red triangle. And the red triangle here, we can do a little bit of deduction, has a base of 40 and a height of 10. So 40 times 10, but remember we gotta take half of that. So 40 times 10 is 400, half of that is 200. So the area of the triangle is 200. So if the whole big rectangle is 1,200 and the small triangle is 200, well, we're just taking 1,200 and we're getting rid of 200. So the area of this composite shape is 1,000, right? The area is equal to 1,000. Yeah? Does that make sense? I hope so. Right, we just took a big simple shape and subtracted and cut it away another simple shape from it, and what we got was a more complicated shape in the end. Right, we got this sort of trapezoidal, but with a dent in it sort of shape. I don't know exactly how to describe it. Looks like an envelope. Okay. Homework 4 is going to be from the textbook. It's across 3 pages, but it's just these problems. So looking at page 528, 529, and 530, I want you to do numbers 7, 8, 11, 12, 13, 16, 17, 18, 19. So do all those problems, and you should be good. Now, they can be a little bit of a challenge. Some of them are especially, but I think you'll actually enjoy them. And I'll say finding the area of composite figures is perhaps the most practical skill you'll learn in math outside of, basic addition and such for, keeping track of your money, right? Finding the areas of shapes, finding the perimeters of shapes, working with shapes can be hugely important. My dad owns a carpet business, and we install carpet all the time, so we often have to figure out the area of sort of uniquely and weirdly shaped rooms, right? So being able to do that is an incredibly useful skill, and it's something you will use a lot in your life, especially as you grow into be an adult and start, building things and furnishing rooms and renovating rooms and doing all that. So I think you'll enjoy it, and if you don't just know, well, it's really useful anyhow. But knowing you, Harley, I think you'll actually enjoy finding some of these areas, the challenge of it. So good luck. That's all I have for you now. I'm going to have a quiz in conjunction with these 4 homeworks. Take your time on it. There's a lot of it. I don't expect you to have this done on Friday. If you need to take the weekend as well, feel free. No worries there. And even maybe, let's just put it a nice due Tuesday. That should give you plenty of time. So 1 week from tomorrow. Okay. Let me know if you have any questions or anything at all. I can Zoom. We can talk over the phone, whatever you need to. But I know you got a lot of support there. But whatever you need, man, let me know. Okay. You have a good rest of your week, and I hope it's nice and sunny down in Florida. Have a good one.